Okay, so we're going to continue on our journey through basically how we mathematically set up the problem and then take the data and then use that data to figure out what the image is. And in the example, remember, we're in a two-dimensional plane. We're forgetting about the z direction right now. We just have a two-dimensional image. And this would be the patient's chest, their back, their left arm's over here, their right arm is over here in traditional sort of orientation. The image that we're going to create is an image of the linear attenuation coefficient, and that is the relative ability of X-rays to be absorbed by that tissue. Okay, that's the image that we're going to create. And we've set it up mathematically such that we parameterize the data that we're obtaining with an angle theta, which is the projection angle through our object. So as theta goes here, we get different projections through the object. And L is the distance of this projection line from the origin. Okay, so we have theta and L that parameterizes the two dimensions. All of the points in the XY plane along this line go into creating this single data point, right? And it's parameterized along here by L, the angle theta, and the data point that we're going to achieve is after we have our measurement we've taken for this patient. We take a measurement in terms of the intensity of the X-rays that hit the detector here. We divide it by the intensity of the X-rays. We would see if there was nothing there, it was just air. So we get a number less than 1, between 0 and 1. Take the log of that and make it a positive number by putting a minus sign here, and you get this is the expression of what this is. You've transformed your data with this log and normalization, and it's equal to this term, which is terrific, because this term is just the sum of all the mu values as I traverse the patient, right? So if we think of it, instead of in a continuum, think of it in a discrete sense, we'll divide this image up into little boxes, and inside each voxel or box, we're going to have an average mu value for everything in that voxel or box. And we can just add up those mu values for each box that we cross, right? And that's a very nice arithmetic thing to be able to say. So we have this now, we've got this function g, and it's parameterized by, or the position is parameterized by L and theta. So we get g L theta here. We have to figure out how, from our measurements and manipulations from which we've created g L theta, do we get back to the source mu xy, which is the patient, or the image of the patient. That's our goal. There's a fine point here that is worth looking into. Some people might choose this for their project. I think I saw some people already have probably. And that is all of this mathematics assumes that for different L's, we have straight lines that are parallel to each other. So when I set theta, I get a whole set of L here, and those trajectories through the patient are straight lines that are all parallel to each other, okay? And that's called parallel beam geometry, right? It's simple mathematically. And so for a given theta, I just have a bunch of parallel lines. I integrate mu along each of those lines and store that data for a specific theta value and for all my L values along here. I click the scanner to a new orientation such that the parallel beams now are at a new angle, 120, right? And I just take those measurements and put that in my GL theta function as theta equals 120. So let's plot GL theta in a theta plane here and an L dimension here. So I've got theta on this axis, L on this axis. For each theta, in this case 90, I just plonk down all my values that I measure as a function of L, change theta to 120, plonk down all my values on L, right, for that angle. And in doing that, I'm going to build up a two-dimensional function in the plane, in this GL theta plane, right, that represents all of my raw data. Okay. What actually happens in a CT scanner, this is what happens in mathematical CT, or when mathematicians were figuring out the projection slice theorem and all of this stuff about projections in CT. They look at this. But what's happening in our machine is we have an X-ray source up here, and it has a little porthole, and all the X-rays come out as a fan beam, right? And it's very efficient because I can take all of these data simultaneously, right? So I still have a detector down here, and we're going to call it L, right? And for what does theta equal 90 mean? In this case, it means whatever the angle is of the central beam in my fan beam. That's going to be our orientation, okay? So that means when I take this view, the X-rays come out and I take this view, I get for this pathway, theta is equal to 90, right? And it's that detector for this acquisition that has theta equal to 90. It's just one detector, right? So I go over here and I say, okay, if theta is 90 here, that's this value. It's right in the middle of all of my values that I'm recording. If I go to smaller angles, which are these arrows, so here's 90, less than 90 as I go this way, I plot whatever value I read out on my detector, but it happens at a different angle, right? So I get all of these angles across here simultaneously. And then the whole shebang rotates because my source rotates, my detector rotates, okay? Such that now the central detector straight through the phantom is at 120 degrees, and that's this point here. So this center detector here is this here. And then if I go to higher angles, I map out these points. If I go to lower angles this way, I map out these points. So I am mapping out a two-dimensional measurement of GL theta, right? I'm still doing that. However, I'm just doing it on these diagonal lines, and I grab each one of these lines simultaneously, and that's how we're going to fill out GL theta. Okay, that's called fan beam orientation. The mathematics is, as you can imagine, I've got a whole set of points here. I can just map it down onto 2D and do a transformation of my data such that it goes back into this GL theta where I'm measuring for a constant theta different L values. The deal there is there's some interesting things, right? Because this point, as I go down, it's at the same theta. So when I go down as a function of L here, those data points were taken at different times, right? Because all of the simultaneous data occurs across here, across the diagonal, when all of the data gets sampled here. So then when I move the angle and go to this, there's a delta t between taking this point and this point, right? So as a function of theta, my data is taken at different times, which leads to interesting motion artifacts. Okay, well, we did all that on the last page. So the thing that we're going to solve for, did we do this last time? This mu calculation? I don't think we did, right? If this was all done originally in the early 70s, right? And so computing back then, you had like a HP little calculator or something like that, if that. And so they needed to encode the image as integers, and ideally sort of 8-bit integers or maybe 10-bit integers, something like that. And the mu values, as you saw from the NIST table, they're like floating point numbers to 16 digits, right? So we need to map to a better system for putting up numbers on a screen in the 70s, right? And so what they came up with is this, and it's the mu value of your pixel minus the mu value of water divided by the mu value of water. So it's like the fractional change in mu compared with water is this term multiplied by 1,000. And that's going to give you a kind of 4 digits. They're going to be integers. You're going to go from minus 1,000 to whatever, a high number, right? And that's easily encoded, digitally. And so that's why we're here. These are called Hounsfield units, right? So air, as you can see from the formula, the effective mu in air is 0, right? So it just doesn't stop X-rays. And so you get water over water is 1 times 1,000. It's minus 1,000. So that's air. It's always minus 1,000. And then water, you can figure out what water is, right? It's mu of water minus mu of water divided. So it's 0, right? So in every CT scan, when you put a region of interest on the water, it's 0. And when you put a region of interest on the air, it's minus 1,000. And you calibrate your scanner every day such that that is true. So every day they put water in the scanner and they image it. They put an ROI there, and the underlying engineering, the machine goes, okay, that's my water for today, just in case there's some kind of drift in the X-ray power or something like that. So everything's normalized to itself, basically. And they scan air as well. So this is always true. So here's a list of these Hounsfield unit numbers in different things you would see in humans, like soft tissue, cortical bone. So you can carry these numbers around pretty easily, right? They're just like 4 digits. That's pretty cool. It's easier to look at it. Here's a CT image of a chest. It's a heart, myocardium, blood with contrast in it. That's why it looks bright, is because the contrast is in the blood. There's bone down here, lung, etc. And if we look at what the Hounsfield units are of those tissues, in the myocardium, which is just muscle, standard muscle, the Hounsfield unit's about 120. Okay, so that means the attenuation is slightly more than water, right? If it's positive. Okay? Yes? How we're going to measure mu? Well, we're going to, when we make the CT scan, right, it turns out that from the math here, right, our GD measurement here is actually just the sum of all the mu's in that column. So when you make a floating point image, it comes out as mu's. Those are the things you have. That's your image, right? And it comes out from the fact that you measured this thing. So that's the underlying picture, is these mu's as a function of position. And then before you display the image, it's transformed into this Hounsfield unit number. But you can at every point. So if I have 120, you can use that formula to figure out what mu equals at that point, because you know what the mu of water is, right? And so you can just calculate it. Yeah.
And that on this image, the fat has like a negative 120 issue, and how do you like? Well, what is the interpretation?
Sure.
Color seems very similar to. It can be similar to some like other positive issue number. Like, how do you distinguish that?
Okay, so the question is, fat in this image seems to have a Hounsfield unit that's negative. How does that happen, number one? And number two, isn't this contrast very similar to this over here? How do you distinguish them? Right. Okay, two very good questions. It gets to be minus 120 because its mu value is less than water. Okay, so when water gets subtracted in that formula here, so this number is smaller than this number, it becomes negative. Just like when this is air, this number is 0, right? And the mu value of water is not 0, it's a positive number. And so that becomes minus 1,000. For fat, it becomes minus 120, right? So that means fat attenuates X-rays compared to water, does it attenuate more X-rays or less X-rays? It attenuates less X-rays, right? So it's more like air. It's going towards the minus 1,000, right? And for something that attenuates a lot of X-rays, right? Say this was a piece of metal or bone, right? Then its mu value is much higher than water. So this will be a big number, right? So that's when I come here and I look, what has a big number? Well, the blood in here, and now the mu values are different enough that it's easy to see that this tissue or this substance, this blood, is not the same as this, right? You can do that with fat and myocardium, but you have to change the way you display the picture such that this number and this number look quite different in the picture. You can achieve that, right? And I'll show you. You just narrow down the width of values that you're going to display such that things above it all turn white, things below it all turn black, and then you see contrast in those regions. Here we've put the contrast such that we really want to see the details in things that are way up at 650, right? So it's wide open. Skeletal muscle, slightly less than myocardium at this time. That could be because some of this contrast went into the myocardium. So in the vascular structures of the myocardium, this contrast flows in there, and it will raise the signal of myocardium when it's in there. Not much, but it does it. 650 is a large number, right? The normal Hounsfield unit of blood before you put contrast in it is like 100 or maybe 60 to 80, something like that. And so when the contrast goes in, it really brightens it up, as we've seen on many demonstrations. This is a wire, and it's like a pacing lead, or not a pacing lead, it's a ECG lead, okay, just to measure the person's ECG. And the Hounsfield unit there is 5,000, right? So that mu value was really high compared to water, right? 5 times greater. Yeah. Oh, down here? That's a great question. The question is, what are these bright spots? Does this person have leads in their lung? That is vessels in the lung. So your lung is just filled with both arteries and veins, right? Or coming back to the heart. And so when the contrast is in those small vessels, they light up. What else is interesting? Oh, the cortical bone, 750, right? So it's almost twice what water. Here, if we go down and look, so this is where we're changing the center and window of our image so that we're just going to look at the contrast in the lung. Now everything here is kind of bleached out. We can't see it because its values are being displayed as white. So in the lung, you can see now all these tiny little vessels, big vessels, little vessels, and they're filled with contrast. You look at a place in the lung that doesn't seem to have a lot of features, so no large vessel is there, and the attenuation is minus 800. So it's almost air, right? But not quite. There's still stuff in there, a little bit of, very small vessels and things holding the contrast. When you look up here above the patient's chest, you do get minus 1,000 in the air. So that's truly air. And that's about it. Oh, the other interesting thing is this little piece of material there is a calcification. And usually when you have some kind of injury to vascular tissue, as it's repairing, it deposits something very similar to bone as it's scarring over and repairing. And so you can see that repair bone or calcification in the vessels. As people get older, they get more and more and more of this stuff, right? So that you see calcification all over their aorta, up and down, and in their coronary arteries and in their carotid arteries. You just get all this bony material in your bloodstream, and the stiffness of your vascular wall. You guys are all really young, so your vascular wall is like really pliable. So when you exercise and your pressure goes up, it'll expand nicely and stuff like that. As you get older, it gets stiffer and stiffer until finally, on some autopsies, when somebody's really old and they pull out the aorta, it's just like crackling. It's really all calcified up and really stiff, right? So anyway, that's how it goes. We did this briefly, right? And so if we go back to what we want, GL theta is what we measure, or we create from the measurements, we create GL theta, and we want to go back to mu. The fundamental relationship is that our data, G, is the sum of the mu values through a pathway through the patient. So we looked at this really simple example where here's our patient. We're going to make a 4-pixel image, 2x2 image of this patient. Okay. So we want to estimate mu at these 4 locations, right? To do so, we take projections. So we set our angle and we project x-rays this way, right? And we get a measurement here, G1. So we're going to take the measurement. We'll divide it by the measurement we got when there was nothing there, right? That I naught. And we'll take the minus log, and that gives us that G value right there. And so we know from what we derived before that this G1 is equal to mu1 plus mu2, just by definition and by the way we've constructed this thing, right? X-ray comes through here. We make this measurement. We know this measurement is equal to mu3 plus mu4. We'll project this way and get a third measurement. We know that measurement is mu1 plus mu3, right? And we'll project this way to get G4, and we know that is equal to mu2 plus mu4. Okay, so we've done basically 2 angles through this object. We've got a horizontal one, a vertical angle, and that's given us this set of equations here. And from your linear algebra in first year linear algebra, when you look at this and you say, oh, I've got all these numbers, I need these ones, that's just an inversion, right? That's just matrix inversion to solve for the unknowns. I've got 4 measurements, 4 unknowns. So I've got 4 equations, 4 unknowns, should be able to solve for those unknowns. And the way you do that is you set it up like this. You rewrite this thing as a matrix equation where you have a vector of your measurements, you have a vector of your unknowns you want to solve for, and you have this matrix that you have to invert in order to get mu1 equals whatever, right? Interestingly, if you're really good at linear algebra, which I'm not, I'm just average, you look at this set of equations and you would say, something's wrong here. I can derive one of these equations from the others, right? So one of these equations, or all of them actually, is dependent on the 3 others. I can just make that equation. And so we don't have enough information actually with this set of measurements to solve for the mu values because of that dependence. And so this, in linear algebra, you say this matrix is not full rank, right? It doesn't have full rank to do this inversion. So we need actually to make a new measurement at a different angle. So we took this angle, this angle. We also need a measurement at this angle, right? To get rid of this dependence. So this equation here, P4 is 1 plus 2 minus 3, you get this one. So what we can do is we'll make another measurement along this way and rewrite it. We'll call that P5 such that we get mu1 plus mu4. And now this is a full rank set of equations and we can solve for the mu values. So that's it. That's CT, right? We have the sum of the mu values through these angles, right? I just take as many angles as I need to get as many mu values as I need, right? So if this was a 10 by 10, the equation this first equation, P1, would just be mu1 plus mu2 plus mu3, but out to 10. And then I go to the next one and it would be, 10 mu values. If I go to 100, it starts to get pretty big, right? So now my measurement is the sum of 100 numbers, right? By that many equations. And so if we go to a 512 by 512 image, we basically have 262,000 equations. Okay. That's how it scales up. Doesn't scale up linearly. And so you have this 262,000 by 262,000 matrix to get a 512 by 512 image after you do your matrix inversion, right? And so that's hard because the measurements are noisy. So the inversion algorithm's a little unstable when you have noise and stuff. So usually that's not what is done, or historically that's not what is done. But this demonstration shows you that, oh, I have enough measurements to measure every mu value in this plane. So that's what I want, right? I can solve for those mu values, theoretically, right? So they come up with a simpler way to estimate an image based on these measurements, okay? As opposed to doing a huge matrix inversion, let's come up with some simple way to estimate what the image is. And this is called naive backprojection, or simple backprojection. And now we've got a new image that we're going to talk about. And the image is 3 by 3. And it has zeros in all of these guys, in 8 of them, except for the middle is a 3. Okay. And let's see what our G values that we just calculated from this. Remember, we projected through and got a G value was mu1 plus mu2. Can do it here and say, okay, this G value is this plus this plus this. So it's 0. Okay. This G value is this plus this plus this. It's 3. Okay. This one is 0, etc. I go this way, 0, 3, 0. So I can make all of these measurements, right, in this 3 by 3 matrix. So let's look at these data that we've achieved, we've got, and what's the simplest thing we can do to try and estimate what the actual pixel values are. If I look at this line, I know that all of these add up to 3, but I have no idea in what combination they add up to 3, right? I just know they add up to 3. So it could be 3, 0, 0, 0, 3, 0, 0, 0, 3, 1, 1, 1, 1, 2, 0. It's a lot of possibilities. So let's just pick the simplest one. Let's divide up the signal that we've got it from this projection and just project it back equally to every voxel in that projection. That's like the easiest guess we can make. They're all the same, right? So we do that. And so our first estimate from this set of measurements, right, is that we project the 0 back, everybody's 0. We project 3 uniformly across there. So I get 1, 1, 1, and project these back and everybody's 0. So that's our first data point. Now let's take, who goes next? Okay, this one goes next. All right. And we'll say, we're going to project everybody back this way equally, right? So I go through here and I say, well, I have a 3. How can I distribute the 3 equally? Well, I'll put a 1, a 1, and a 1 here. I've already got a 1 in this box, so that becomes a 1, 2, 1, right? Just to add it on there. And the next one we'll look at is this vertical projection. So this is going to project back zeros everywhere, so that doesn't change. This one is going to project back zeros, so they don't change. This one projects back a 1, a 1, and a 1. And so now I've got something building up in the middle. And then I do it exactly the same thing for this. Project back, I get a 1, a 1, and 1. This was already 3, becomes 4, right? And and I'm done. So I've got my 4 views, right? And I've done this simple back projection. And this is the picture I get. That's not bad when you think about it, right? It's like got a big peak in the middle. The background's flat. So it's not so bad, right? It's wrong because this is the actual object, right? So it's got this stuff in the background that shouldn't be there. It's like elevated background. But it has a spike or a peak where the peak should be. It's just the wrong size, right? So it's not a bad guess. That's called naive back projection. And if you do that, not just for a 3x3, but for a large, say 256 squared, and you take 256 projections, right, such that each projection produces, if this is our profile, so we have, I'll give away the answer that the object is a disk here. So when you do a projection through that, you get zeros until you get to the disk, and then you get this projection of a disk, right here. And then you get zeros. And then when I change the angle, I get exactly the same function. It's just the position of the disk shifts, right? Because this is a tremendously simple image. And so at each view angle, I get a new position of that disk. And we do exactly what we did with the previous example. We just take this projection and evenly distribute it back on the image, right? So this stuff projects down to positive signal here, and all of this stuff projects down to zeros, okay, for this projection. And you can see as I'm doing more projections, I'm going to build up a very strong signal where my disk is. And it looks like this. The final image looks like this. There's a couple of things that are wrong in this picture. One is there's a smoky background that isn't there, right? That shouldn't be there. Also, the disk itself isn't just a nice circle with a constant amplitude. It's some kind of blurred peak, right? And so those are the two things that are getting in our way of this simple back projection working. So we looked at this example, and this little demo here shows the projection of the GL theta for a specific theta, and then L would be along this direction, right, for this view, and we're projecting all of those values back, and we'll do that for different angles, okay? And this is what happens when you do that with all of the raw data. You eventually project this back and get a decent picture, right? And if we go back and look at what's happening here, so this is just one view, maybe 2 or 3, 4 or 5, 6 views, okay? So now we have a lot of projection views that are going through the sample sort of on the angular left-right axis or this axis up this way. What does it give us? When we project that back, you can see that we have a really good idea of where this edge is. We have a good idea of, say, this edge right here, right? So it's giving us a lot of information about certain edges in this object. However, if I ask, where is an edge? If I was to draw an arc and find an edge over here, I have no information at this point about where they are, because all I have thus far is added up the views that are at the angles sort of going across this way. As I go to 90 degrees here, now I've got views, I'm projecting views down this way in the sample, and I can tell you something about the edges in this direction, right? Because my projections are going down this way. I still have these edges over here. There are some directions, like this way, I don't have any edges yet. Then I rotate around more until finally I've gone to 180 here, and I've pretty well got all my edges figured out at this point, right, as to what's there. So this is actually using the back projection. It's called convolution back projection, and we're going to figure out how to do this, right? This is obviously not that back projection we just looked at where we have fuzzy stuff in the background and stuff. We're going to learn how to do this convolution back projection. So let's get used to GL theta first. This function here is the GL theta function that is generated when you scan this object. Okay, so this is in the XY plane here. what we're going to do is start at theta with small values, and the theta values get larger as we go this way from top to bottom. The L values along here, these are our positions on the detector. Okay, so that's the L value. From here to here is what gets measured out on that detector as a function of L, right? Or we just parameterize its location as L. So if we look at the object itself and what these different projections or integration of mu through the object look like, we can make a couple of observations. So let's take a look at this single projection. So it has a single theta value, right? So I've my source and my detector are at some theta, right? That center line is pointed in some theta direction. And I have, if I read across here, these are all my measurements of the sum of mu as I project through at that angle. And so just looking at the GL theta function, you can determine a few things like what angle we must be looking at, right, for this function. And so you can just think in your head for a sec, how would I figure out, looking at the object, right, on the right side, and looking at GL theta, remember, this is L, theta is fixed. We're just click to a theta and say, well, which theta do we click to before we measured this L, which is the integration of that object, right? And so here, you can see this oscillating sine wave here is basically the edge of this object, right, at different angles. So when it's at its widest location, that must be between here and here, right? And I'm projecting down this way, right, to get the integrals to fill up the most of L that we can fill up. That's the widest projection of that object. So therefore, if I look at this and say, well, when does the projection of this big part of the object narrow down the most, right? It would be whenever it's the thinnest, which would be in this direction, right? We're projecting down in this direction. And now there's one last thing to figure out. It's like, I've got two of those, got this thin part and this thin part, so I'm going either left to right or right to left in this projection, right? If this is L equals small number up here, and this is L equal big number up here, I look up here and say, okay, L is 0 here, it's big number up here. All this junk here, so on this side, this seems pretty clean. There's a bunch of junk over here when I go from L0 to L large. So that's this junk down here. This stuff is here, right? This is free, it's empty. So that gives no projection back onto the thing. So it must be this one. So I've got L is little, L is big. I've got this junk projecting back onto my detector here, and the main phantom projecting into this space here, right? Some of the interesting features inside the object, it was a very simple object, right? If we look and say, okay, when does this angle happen such that I'm projecting parallel lines this way, right? Can we figure that out? Well, it's when these two dark signals, which are these features here in the GL theta function, right? This one and this one, when they cross, right? That's when we've got this angle, right? They're overlapping, and so they overlap here, right? So that gives you, oh, that angle, that's what's happening. So now you can look at GL theta and say, well, what the heck are these points? Like, do they mean anything, or how do you parameterize them? Well, you can see that this guy and this one, when you plot it out, it's basically a sine wave, right? It's an oscillation that's a sine wave. And it's just as we rotate our detector and our source, and I look at any point in this plane, what I'm going to see is a sine wave as I rotate around there, right? And the sine wave will get a higher amplitude or a bigger throw the farther away it is from the origin, right? Because it'll get thrown back and forth across my detector. And stuff towards the middle are going to be down in here at L values that are right in the middle of the detector. So this thing is called a sinogram. And if you really know CT, you can look at the sinogram and take a guess what the picture looks like. But that's very hard, right? It's extremely hard to do. Oftentimes, if the picture has artifacts on it, as we'll see, it's got something wrong with it, you can look back at the sinogram and it'll tell you, like, oh, what went wrong? And we'll take a look at a couple examples of that. So this is GL theta over here, and this is mu xy that we've got, okay? So here's another example. What are we doing here? Yeah, so this is we've got a lot of little points with different diameters or little discs with different diameters. And so when you look at GL theta, and in this case, L is going this way, theta is going this way, you get a very complex pattern. It's not as simple as this because the features are much finer and they start overlapping with greater frequency, right? So there's a whole bunch of stuff over here. And so you can see all of this overlapping signal. And when you do this naive back projection, so all we're going to do is back project those GL theta values. So here I have G. This, remember, is L. It's all XY points that satisfy this thing being equal to L. And theta. So I'm just going to plop that value down on the plane. And so for a specific L, it's all the same value, right? And they're all oriented at theta. If I do that for every theta, so I just click around, I get this picture for this object, right? Again, not bad, but it's got all this smoke, all this stuff that shouldn't be there. Plus, all of these things are a little blurry. But this thing is worth remembering. It's called a luminogram for some reason, but it's just the sum of all of these GL thetas, right? There is a MATLAB thing. It's only 100 lines or something. It's really simple, in which you can put points in the XY plane and look and see what the GL theta is for those simple points, right? And I want to give away the punchline, but for any point in the plane, its GL theta is basically a sine wave of a different amplitude, okay? All the frequencies are the same, just the amplitude changes because you're just rotating around once, right? Okay, so we're gonna look at this is really cool math that was derived by radon. Do you remember we had those four peoples? There was radon. What's the guy who worked for me? EMI, Hounsfield, etc. So they all worked out this math independently, but anyway, here we go. So there's a really interesting thing that was proven called the projection slice theorem. It was proved mathematically at the beginning of the 20th century. And what it means, and we'll change our notation to the course notation, but in the book, I think this is how it is. So if you have an object in the plane, whether it's a person or a grapefruit or anything sitting there, and it has a pattern, fxy. So it's got some features, fxy, right? When you do this integration of that pattern and plop that down here as the value for that projection of the object, we get this function, GL theta, right? So we have L this way, theta is fixed. We've fixed theta, it's that projection, okay? If I take the Fourier transform of this object using L as the spatial variable, and I go into spatial frequencies, so I take the Fourier transform with L as the independent variable, what happens is I get another function, one-dimensional function over here, right? And if you look at the Fourier transform, the God-given Fourier transform of this two-dimensional function, f of x, and that's this function here, f of mu and u, right, in spatial, sort of spatial frequency coordinates. This line, when I took this one-dimensional Fourier transform, is a line through that two-dimensional Fourier transform. It's like a sample of that two-dimensional Fourier transform along a line. So if you're confused, that's okay, because it's not intuitive. To me, it's not intuitive, right? That I take any old function, I integrate its values down these lines and create this projection function. I take the Fourier transform of that projection function, and I get a sample through the two-dimensional Fourier transform of that object. That's called the projection slice theorem. It's really pretty cool that it works, right? In the book, online prints and links, you can show, he proves in the book that that is true, right? And you can do that just by wise and systematic changes of variables and things like that. You can show just algebraically that it works out, that it's true. We're not going to do it right now. You can read this proof in the book. It's like starts at equation 615 if you're so inclined. You don't have to be able to prove this to do well in the course, but it's a fun little exercise to go through and show that the Fourier transform of the projection is a line through the two-dimensional Fourier transform. Okay, so this is what it is mathematically in the book. These are the coordinates we use in this class. This is just changing labels, okay? Instead of fxy, we're going to create an image that is mu xy, that the attenuation coefficient as a function of space. This is still GL theta, okay? Theta is the projection angle. The Fourier transform of this is going to be cap u, and the spatial frequency variables are ky and kx, and they're given in radians per meter or cycles per meter. Okay, they're spatial frequencies. And you can, if we have this function and we get its God-given Fourier transform here, we know, suppose we precisely know this function, we take its Fourier transform, we can write it down in these rectilinear coordinates. We can also write it down in circular coordinates or polar coordinates. Okay? And it's a natural thing to do because, recall from the projection slice theorem, when we took the Fourier transform, it was a sample through the origin along some radial vector of the Fourier transform. And so we're going to start thinking about the Fourier transform in this space, basically in polar coordinates, where I have k is the distance to some k value, and theta is our direction in the spatial frequency space, okay? And what that tells us is that the Fourier transform of GL theta, right, as a function of L. So I'm taking this Fourier, I set my k vector. This is as a function of L, this integration. So that's the Fourier transform of this thing. Gives me this function, which is the Fourier transform as a function of distance, or k, from the origin at a specific theta. Okay, so theta is just set in both of these. We don't integrate over it or anything. It's just given to us. Here we take the Fourier transform with L, and that gives us this thing, which is this function right along here. Okay. You can prove by example to yourself that the projection slice theorem is true using some simple functions, right? So this is a function we've seen before, which is the rect function, and it's 1 inside a unit square and 0 outside. And so if we project this function down this way, right, we get GL theta looks like a rectangle, right? And then when you look at the Fourier transform of that, it is this sinc function that is just the Fourier transform of that rectangle. So that works. That's kind of a trivial example where you project through a rectangle, you basically get a rectangle, and its Fourier transform is follows the projection slice theorem. Okay. Now, there's another example where we angle our projection at 45 degrees of the rect function. Okay, so now when we take our integration, if I'm at 45 degrees and I'm projecting down this way, right? Those, what's going to happen now is my integration is not going to be a rect function, right? The integral will be much larger here, right, than it is out here. So it's actually going to be a triangle function, right? Because you can see if I put a line along here and I integrate down here, I get a triangle function. And then, so here's your triangle function, which is the projection at that specific angle of the rect function. And we can compute essentially the one-dimensional Fourier transform of that triangle function and see if that is what is in the 45-degree direction for the Fourier transform of the 2D rect function, right? That's the demonstration that the projection slice theorem works for this 45-degree angle. So you can do that too. If it's just a lot of algebra to get through it, but it works. So those of you who like Fourier space are probably wondering, well, if I now have this GL theta, which is a projection of my object, and it's a sample of my image that I want along a line in Fourier space, why don't I just sample these at different angles, because I'm going to create just multiple angle samples, and then do the inverse Fourier transform to create the picture, right? Because I've got the Fourier space of my image. That's pretty darn close to your image, right? If you got the Fourier transform of the image, just do the inverse Fourier transform. That will get you the image, right? That's what we do in MR. So one way of doing it is I take every data point that I have achieved, and the way you do that is your GL theta are the things you've created from your measurements. You take the Fourier transform as a function of L. That gives you now a set of points through here. So I just have numbers in the Fourier plane. I could interpolate those numbers onto a rectilinear grid, right? So for any point on this grid, say here, I go back here to that same point and ask, how can I estimate what my value is there from the values around it that I have actually measured? So that's just an interpolation problem. You just pick a point here and say, well, from my data, what can I tell you about this point here? Some of those points you have, right? So this one here, I do have like here. We have exactly the point, but other points on the Cartesian grid you don't have. The interesting part about this also is that as we go farther out in Fourier space, our density of points gets lower and lower. So eventually, if we go far enough out, the data that we have measured and created, will be so far apart that it'll be hard to estimate something out there. So it gets harder as you go farther and farther out, right? That's one issue. As we go towards the origin, we get a much denser sampling. So we have much better estimates as we go to the origin, right? But we have to correct for the fact that there's more signal power at the origin, and we'll see that in a second. Okay. Uh, in order to do this inverse Fourier transform method of reconstruction, we're going to, instead of interpolating onto a grid, we're just going to say, you know what? Let's do the Fourier transform in polar coordinates and just use the data we've got. How's that going to work out? So here's the data we've got, right? This is, I'm sorry, scratch that. Here is the relationship between our picture that we're trying to create, our God-given picture, its rectilinear Fourier transform in space that looks like this, okay? So that's what it looks like as a position of kx and ky. And this is the inverse Fourier transform, right? So there's no negative here. This gives us the inverse Fourier transform that goes back to mu xy to reconstruct the perfect estimate of mu xy, right? We can transform this Fourier transform equation into polar coordinates so that we can use the values that we've measured. We don't have to interpolate. We can just take the values we got. So remember, GL theta just gave us these lines across here. And so these are, for a specific theta, you just let k get bigger and it takes you up a line like this. So this is the polar representation of the Fourier transform of our object, and it is directly from the data that we have obtained. Okay? When we take the inverse Fourier transform, we need to transform the Jacobian of this integral such that we're in polar coordinates. So we're going to define kx as x cos theta, ky as y sine theta, and the Jacobian dk d theta isn't just, you can't just write dk sub x dk sub y, doesn't become dk d theta. It becomes basically k dk d theta. Think back to first year calculus when you mapped things to polar coordinates and did the integral around some circularly symmetric object. Your Jacobian was usually, r dr d theta, right? And so that k shows up there for this integral to do the inverse Fourier transform. And this k makes all the difference, right? For actually getting the image, the true image from our raw data, this k is the thing that makes the big difference. Yeah?
Does that mean like the K is always the same? Like, I guess it's just like in the polar coordinates, is it always a round circle instead of a circle?
Yes. Yes. So in we're going to do polar coordinates where we just have a circularly symmetric sampling of this thing. Yep.
That when it gets outside that there's less, are you talking about there's less measurements taken at those points, or just it's less energy and signal there?
There's less. So the question is, as we go out here, what does it mean that there's less data right out here? So there's less data density, right? In that if I go in here and ask how far apart are my measurements, if I'm trying to interpolate a point there, how far away are the points that I'm going to use to make that interpolation? Well, I've got 4 points very close to me here to make that interpolation, right? As I go farther out here and say, well, how far apart are the points here? They're just a greater distance in Fourier space away. So we probably aren't estimating this point with as high precision as we can estimate this point down here, right? Until finally you have an undersampling problem at a really high frequencies because you haven't taken enough angles, right? Okay, so basically this also shows that GL theta, right, plus if theta plus pi. So when you take GL theta, I project down. If I tip over such that I'm 180 degrees from that, the data, all that happens is there's a reflection of the data. It's the same data, right? So GL theta plus pi is just G minus L theta, right? So that's for every view in this case. And that gives us this symmetry here, right? That G of K theta plus pi is just G of negative K, right? So, okay. So here's our filtered or our back projection that we're doing using a inverse Fourier transform with the Jacobian in here. We'll bring this K term, bring it up here, right? And substitute L in for this value here. And we can do the first integral, right, over dk. And so when we look at that, right, we have done basically a Fourier transform of this function here. So it's the inverse Fourier transform, which is this when I do this integral over dk, right? We're just fixing theta. I am essentially from here to here doing the inverse Fourier transform of k times gk theta. Remember, this is the stuff I have. I've created it from my raw data by doing the Fourier transform and getting over here. This is my Jacobian. And so when I take the inverse Fourier transform with respect to k, I get to this middle step where I now have a new function, and we're going to call it g star L theta, right? And this final integral that we're doing to achieve this inverse Fourier transform, this final integral, is basically just a back projection, that naive back projection of these g star L thetas. Right? So we've got GL theta, G star L thetas, and for every theta, we're just adding them up, which is what we did for the naive back projection, except we're now doing it with this function and not GL theta, right? Do I have that? I might have it. No, I don't. Okay. Yep.
I didn't understand the thing. So the naive is the same thing, but in
Yeah, it's so this Fourier transform here, or inverse Fourier transform here, if, for example, I take this k out, right? Just take it out of this integral. So then it's just the inverse Fourier transform of gk theta. And that just takes me back to GL theta, because that's how I got gk theta, right? What happened was when we went to polar coordinates, this k shows up. So we put that here when we're doing this inverse Fourier transform. And now I have not an inverse Fourier transform of gk theta, which I got from my data. I multiply it by this and do the inverse Fourier transform of that product, right, of k times gk theta. And so that gives me something related to GL theta, but we put a star there because it is not GL theta. It's this thing. Okay. And so that's written explicitly here that this G star L theta is the inverse Fourier transform of what we got from GL theta by taking the Fourier transform times absolute value of k. And we remember, right, the inverse Fourier transform of a product, right, is what in the other space? It's the convolution, right? By the convolution theorem, if I have a product in one space, I get basically a convolution in the other space. So to see how this thing is related to GL theta, we can look at that. This inverse Fourier transform is just GL theta convolved with the inverse Fourier transform of the absolute value of k, just by the convolution theorem, right? So that's how this thing is related to GL theta. It is GL theta convolved with a different function. And the function we convolve it with is the inverse Fourier transform of K, right? So K, let's look back, like what is K? I mean, K is a really simple function, right? As you go away from the origin, K just gets bigger. So it's just like y equals x, right? It's just, so as I go away from the origin, it just goes up like y equals x. However, it's in polar coordinates. So any direction I look, it's just going up like that. So absolute value of K in this case is basically just an inverted cone, right? So at the origin it's 0, and then it climbs out like that, right? And so that's what's happening to this function. It's getting multiplied by something that, as K gets bigger, it's multiplied by bigger and bigger numbers, right? As it goes out. And at the origin, it's multiplied by 0, right? So we can achieve that if we know what the inverse Fourier transform of K is. We do, right? We can calculate it. We can just convolve GL theta with that, and that will achieve like this thing here. So the true back projection, not naive back projection, the true back projection to get the exact value of mu xy is the back projection of these things, the G star L thetas. We're going to back project those things, right? Okay, so this is filtered back projection, it's called. And if this is our original GL theta, we took its Fourier transform, we get to GK theta over here, right? So this is our data. We've provided all of this, right? This is the absolute value of K. Over here, it's a function that looks like this. It just goes up. And then eventually, we're going to run out of spatial frequencies to reconstruct, and so it just windows down. And this is called a Romlock filter for the two guys who invented it and came up with this method for reconstructing it. So what we can do, right, is just in Fourier space, we just multiply by K as we saw in the formula, take the inverse Fourier transform of that. That gives us these things, and we just back project those things to get the picture. Okay. There's an alternative way to do this, which we saw, and that is I've got GL theta. I don't take its Fourier transform. I just say that's my data, right? I've got that data. I convolve my data with the inverse Fourier transform of K, right? Which looks something like this. Now I just have a new function, which is the convolution of this and this. It's right here. That equals G star L theta, and I just back project it. So that's two equivalent ways to get to the same place, right? I can do it in the spatial domain with a convolution. Historically, because of cost of computing and stuff, cost of calculating Fourier transforms, this was the way it's done, right? But now it's done both ways. So let's look at an example. Here is GL theta of a disk, right? Remember, it had a 0, 0, 0, and then it had this mound, right? So the integration through the maximum part of the disk, and then it goes down. When I convolve that with the Fourier transform of the ramp of K, I get this function. So this is what G star L theta looks like for this. It looks completely different, right? But there's a couple of features that are great. This thing, even though it was a flat top disk, right, never came to a constant. It just went to a peak and then right back down. This one actually achieves a flat top, right? So that when I back project it, at least it'll be flat. My disk will be flat. It also has these really cool negative side lobes, right? And so all that crap that we had in the background, all the fog that came from just back projecting GL theta, when I back project G star L theta, all these negative things get rid of that fog, right? They subtract it off, right? Yeah. Oh, because if my image is a disk, okay, and it's a constant, say it's a disk with unity and it has a diameter and then 0 in the background. If I take CT data and then I get all my GL thetas for that and just back project them naively, the image I get does not have a constant plateau. It has a peak, right? Like this. It looks like this sort of projected back. And so it just goes down like this. So it's not the object. It's an inaccurate representation of the object. But when we get to this part, we do this convolution back projection. We do the convolution first. It gives me a flat top. It's a single example of how it's more accurately representing an object, in this case, say a disk, right? So here's the object sinogram, right? This is GL theta. This is G star L theta after convolution with that absolute value of K. And a line profile through that, you can see it has 0 mean and it has positive and negative values, right? When you back project those things, this is back projection of G star L theta. This is what one of them looks like back projected. And then when you put them all together, this is 40 of them put together, 80, 120 at different angles. And then you finally get back the actual object, right? So 0 background, disks, the whole thing. Okay. So what are we at? We're at 12:15, so we got 5 minutes. In applying that convolution of this function here, this guy Ramachandran and Lakshmi Narayanan came up with this technique of multiplying, doing this convolution back projection, right? And this is a great name. This is like Lakshmi is super rich, and this is like Narayan is like Vishnu, right? Like super holy and powerful. So this guy's name is super rich, holy, powerful dude. So he better come up with something good, right? And Ramachandran, same deal. I think Rama's like the moon and Chandran is Vishnu. And so it's like moon superpower, right? But then when it's all said and done, the filter is called a Ramlock filter. So it's kind of lost. But anyway, it's like nice lake or something like that. So anyway, you've got absolute value of K here. And the Fourier transform of this thing looks like this. And this is what we're going to convolve our GL theta with, right, to achieve the absolute accurate reconstruction of the image. Comes with a catch, right? There is a problem here. One is you can't, mathematically, K just keeps going to infinity, right? We can't do that. We're not going to amplify our data out and take data out to infinity, right? So we have to cut it off somewhere, right? And so you finally decide, okay, I'll cut it off here at this, frequency. And normally your object has a lot of spatial frequencies, and then they roll off themselves. And finally, you can't image any higher spatial frequencies, right, with your detector and all of that stuff. And so it can even roll down here, but what's out here when the data is gone is noise. And so you are basically amplifying background high frequency noise, right? And so when you make an image with a filter that looks like that, it just has tons of high frequency noise in it, right? It's accurate if you want to get as close as possible to the true values that are in there. It's what you want to use, but radiologists usually look at those pictures and go, no, I can't look at that. It's too noisy, right? There's too much high frequency noise. And so manufacturers, instead of using this ramp filter, a Ramlock filter, they will soften it up a bit. So as we get to higher frequencies, they'll start attenuating the data. And so here's one way of doing it. You just put a cosine filter here. So it goes to like a zero derivative, but it still comes down at a very sharp point. Here's another one. This is called a Shep-Logan, where it's this equation here. So it ramps down even stronger at the edges. And then this one goes dead to zero, right? So we're bringing the filter all the way down to zero. And then a Hamming and a Hanning window. A Hamming comes, it has a zero derivative here, but it still has a drop. This one has a zero derivative and it goes all the way down to zero, right? And you can see the Fourier transform of each one of these kernels. So this is the Ramlock. It has a lot of sidebands on it. And then as we get to these smoother and smoother filters, you can see that this sort of becomes a smoother function. It's more like an averaging function, but it still has to have these negative side lobes, right? In order to get rid of the stuff that's, otherwise would show up as smoke. So here's the Ramlock filter, like the absolute value of K. This is the Hanning filter. And you look up the two pictures and say, which is created by the Hanning filter, right? It's not too hard because the edges of this thing are all blurry, right? So it basically, this has super crispy edges, high frequency edges, but it's going to cause, you can see some artifacts here off the edges and it'll have much higher noise. Here's an example from our scanner here. I put a phantom in, you do what's called a bone acquisition, and that uses something that's very close to a Ramlock filter. It's not exactly Ramlock, but you can see there's a lot more noise, right? So a lot of high frequency data comes through, and there's high frequency artifacts off of very sharp, big devices that aren't on a perfect edge. And this is a more standard, like Hamming filter that causes more acceptable signal to noise for a clinician. Okay,